Hello friends, welcome you all to the 17th lecture on function analysis and its applications. In this lecture, we will discuss the Banach algebra and further theorems on bounded linear transformations. This is the contents, Banach algebra and further theorems of bounded linear transformations. Banach algebra. An algebra is a linear space whose vectors can be multiplied in such a way that if x, y, z is the element of linear space, then it is defined x into y, z equal to xy into z, and x into y plus z equal to xy plus xz, and x plus y into z equal to xz plus yz. And if a be any scalar, then a into xy equal to ax into y equal to x into ay. Okay, because here ax also a vector, y vector. Okay. Thus, an algebra is a linear space that is also a ring in which condition third holds. Okay. We call a complex or real algebra according as the scalars are complex or real number. A commutative algebra is an algebra where multiplication satisfies the condition xy equal to yx. An algebra with identity is an algebra with the following property. There exists a non-zero element in the algebra denoted by 1 called the multiplicative identity element or simply the identity, such that 1 into x equal to x into 1 is equal to x for all x belonging to linear space. A subalgebra of an algebra is a linear space which conditions the product of each pair of its elements. Okay. If n is nonlinear space and also an algebra over C or R, that is set of complex number or set of real number, and if norm xy less or equal to norm x norm y for all xy belonging to n, then n is called complex or real normed algebra. Okay, according as C or R. If a normed algebra has the multiplicative identity U, then we will postulate that norm U is equal to 1. A complex or real Banach space which is also normed algebra is called a Banach algebra. Theorem. If n is a Banach space, then beta n is a Banach algebra with the algebraic operations t1 plus t2x equal to t1x plus t2x, and t1 t2x is equal to t1 of t2x, and a tx equal to a into tx, where a is any scalar. Here beta n is the set of all bounded linear transformation on normal linear space n, and the norm defined by norm t equal to supremum of norm Tx such that x belonging to n and norm x less or equal to 1. Further multiplication in beta n is jointly continuous. Okay, let us prove it. We have seen in the theorem of lecture 16 of this course that beta n is a Banach space if n is Banach space. So we need only prove that beta n is normed algebra, that is, we have to verify conditions first, second, third and fourth of the preceding definition. These conditions are easy and so avoid here. Okay. We prove here only second and sixth. Okay. These are the conditions of algebra. Total 7 postulates. We prove here only second and sixth. We have t into t1 plus t2x equal to, what is the condition second? Here condition second, x y plus z is equal to xy plus xz. In this theorem, t1x plus t2x as y plus z and t at the place of x. Okay. So we have to prove t1 plus t2. Okay. T into t1 plus t2x equal to, as per the statement, this we can write t into t1 plus t2x. Okay. By this conditions, we can write this is t1x plus t2x. Applying this, we have t1x plus t2x. Okay. This can be written as t1x plus t2x. And applying this condition, that t1 t2x is t1 t2x. So here this can be written as t1x plus t2x. Okay. So this can be written as also t1 plus t2x. Okay. Therefore, t1 plus t2 equal to t1 plus t2. So condition second also satisfied. Sixth condition, norm t1 t2 equal to supremum of norm t1 t2 x such that x belonging to n, norm x less or equal to 1. As per the statement here, norm t is equal to supremum of norm tx such that x belonging to n and norm x less or equal to 1. So here at the place of t, here t1 t2. Okay. So t1 t2 can be defined as supremum of norm t1 t2 x such that x belonging to n and norm x less or equal to 1. And this one can be defined supremum norm t1 t2x, okay, as per the statement this, okay, t1 t2x such that x belonging to n and norm x less or equal to 1. So this is as tx type. Okay. T1 is a bounded linear transformation because T1 and T2 belonging to beta n. Okay. So T1 of T to X. So we know that the property, if T is bounded linear transformation, then Tx less or norm of Tx less or equal to norm T norm X. Okay, so using this property, we can write this is less or equal to norm of T1 into norm of T2x. Okay, so this norm T1 is free from x, that is constant. So we can write out of the supremum, that is this one. Norm T1, T2 less or equal to norm T1, supremum norm T2x, such that x belonging to n, norm x less or equal to 1. T2 also belonging to beta n. Okay. So again applying this property, we have norm T2 norm x, and here norm x less or equal to 1. So norm T1 T2 less or equal to norm T1 norm T2. Okay. Hence proved. Second property of the algebra. Okay. We now prove the multiplication beta n is jointly continuous. That is, if Tn converges to T and Tn dash converges to T dash as n tend to infinity, then Tn dash converges to Tt dash. Okay, here that is. Let us prove it. Let Tn converges to T and Tn dash converging to T dash as n tend to infinity. Okay, in beta n. Okay, so here meaning of this is norm Tn minus T converges to 0 and norm Tn dash minus T dash tend to 0 as n tend to infinity. Okay, then norm Tn dash minus Tt dash. Okay, we have to prove it tend to 0. Okay, then we have this one. So we prove it. This term can be written as this. Here we have added Tn T dash and subtracted Tn T dash. That is no change in left hand side. Okay. So Tn common from first two term and T dash common from second two term. So we have Tn in bracket Tn dash minus T dash plus Tn minus T dash. Okay. So here we have two term in norm. So we can apply the triangle property of norm, that is less or equal to Tn dash minus T dash plus norm Tn minus T dash. Okay. So here multiplication of two linear transformation Tn and Tn dash minus T dash and similarly this. Okay. So applying above 6 property. So we can write this is less or equal to norm Tn dash minus T dash, and this one norm Tn minus T into norm T dash. Okay. So here norm Tn minus T tend to 0 and norm Tn dash minus T dash tend to 0 as n tend to infinity. So this quantity tend to 0 and this is also tend to 0 as n tend to infinity. Okay. So this is 0 and this is 0. So total quantity tend to 0 as n tend to infinity. Hence norm Tn dash minus Tt dash tend to 0. That is Tn dash minus Tt dash tend to 0 as n tend to infinity, that is Tn dash tend to Tt dash as n tend to infinity. Noting point, if n not equal to 0, then the identity transformation I is an identity element of beta n such that norm I is equal to 1. Okay, so we have to prove seventh property of algebra here. Norm u is equal to 1. Okay, where u is identity. So here we have to prove norm I is equal to 1. Proof. We have ITX, multiplication of two operator, I and T. ITX equal to I into Tx, applying this property. Okay, so I is the identity, so it can be written as Tx. Also it can be written Tix, and this as again property this we can write Tix. Therefore, It equal to T equal to Ti. This shows that I is the identity element for beta n. Further, norm I is equal to supremum Ix, because here norm T is equal to supremum norm Tx such that x belonging to n and norm x less or equal to 1. So here T is I. So norm I is equal to supremum Ix such that x belonging to n, norm x less or equal to 1. Okay, Ix, that is x, that is this one, norm x, such that x belonging to n and norm x less or equal to 1. Norm x less or equal to 1, that is, this is 1. Okay, so norm I is equal to 1. So seventh condition also satisfied. Next theorem. Let T be a linear transformation of a non-linear space n into another non-linear space n dash, then the following statements are equivalent to one another. First, T is continuous. Second, T is continuous at the origin, that is sequence xn tend to 0. This implies that Txn tend to 0, that is xn converging to 0. This implies that Txn converging to 0 as n tend to infinity. Third, T is bounded, that is there exists a real number k greater than 0, that is positive constant, such that norm Tx less or equal to k norm x for all x belonging to n. Next, if S is equal to x, norm x less or equal to 1, is a closed unit sphere in n, then its image is bounded set in n dash. Okay, so we have to prove these conditions are equivalent. Okay, proof. Here we prove first to second and second to first. Similarly, second to third and third to second, and third to fourth and fourth to third. So if we prove in this way, that is, we can say that all conditions are equivalent. So let us prove first to second. Suppose we have T is continuous, then we have to prove T is continuous at the origin, and converse, to prove T is continuous at the origin, then T is continuous everywhere. So first we take, let T be continuous. Suppose xn be any sequence in n such that xn converging to 0 as n tend to infinity, then by the definition of continuity of T, we have if xn tend to 0, this implies that txn tend to t0. Okay, so t is linear. Okay, so t0 is 0. It means txn tend to 0. Okay, hence t is continuous at the origin. Conversely, suppose t be continuous at the origin and xn be any sequence in n such that xn converging to x is the element of n and xn also a sequence of n. It can be written as xn minus x tend to 0. So this is a sequence tend to 0. Then as per the definition of continuity, t xn minus x tend to t0 converging to 0. t0 means 0. Okay, so t xn minus x tend to 0. By the linearity property, txn minus tx tend to 0. This implies that txn converging to tx as n tend to infinity. So this proves that xn converges to x, then txn converges to tx, that is t is continuous. Second to third, let t is continuous at the origin. We prove here by contradiction. And suppose if possible t is not a bounded. If not bounded, it means there is no real number k to satisfy this condition. Suppose for each positive integer n, then for xn belonging to n, xn not equal to 0, such that norm txn greater than n norm xn. Okay, because t is not bounded for positive integer n. Okay, so dividing both sides by n into norm xn, so it can be written as norm txn upon n norm xn greater than 1. So n is scalar, norm xn also is scalar. So we can write this as norm txn upon n norm xn. Okay, because we know that norm of alpha x equal to mod alpha norm x. Okay, so here n and norm xn as alpha, that is both positive. Okay, so this can be written as norm alpha tx type. Okay, so under norm txn upon n norm xn greater than 1. So again applying this property. Okay, here t is linear. Okay, so also we know that this is type of alpha tx. Okay, so you can t alpha x is equal to alpha tx. Okay, so this is as alpha. Okay, so we can write t xn upon n norm xn greater than 1 using this property. Now set here yn is equal to xn upon n norm xn. Okay, then this can be written as norm tyn greater than 1. Okay, here our setting is yn is equal to xn upon norm xn. Then norm yn equal to norm of xn upon n norm xn. Okay, that is 1 upon n norm xn upon norm xn. Okay, norm xn as scalar and this is norm xn. Okay, so this is outside and this is norm xn. and this one cancel out, we have 1 upon n. These tend to 0 as n tend to infinity. So yn tend to 0 as n tend to infinity, but tyn not tend to 0. Okay, here tyn greater than 1. Okay, here tyn greater than 1. So this is not converging to origin. Okay, so it must be a norm t less or equal to k norm x. Hence t is not continuous at the origin, which is a contradiction. Hence t must be bounded. Conversely, now we have to prove if t is bounded, then it is a continuous at the origin. So let t be a bounded so that there exists a positive number k greater than 0 such that norm tx less or equal to k norm x. Okay, to show that t is continuous at the origin. Let xn be any sequence in n such that xn converging to 0. Then norm xn converges to norm 0, that is 0. Taking norm both sides, so norm xn to norm 0, and we know that norm 0 is equal to 0, that is 0. Also from equation 2, if xn is the element of n, then from equation 2 txn less or equal to k norm xn, okay, and xn tend to 0, it means txn tend to 0. So from equation 2 we have norm txn less or equal to k norm xn. It follows that from 3 and 4 norm txn converging to 0. Hence xn converging to 0, this implies that txn converging to 0, and consequently t is continuous at the origin. Third to fourth. In third, we have t is bounded linear transformation. Okay, so assume norm tx less or equal to k norm x for every x belonging to n, and x be any point of the closed unit sphere S is equal to x such that norm x less or equal to 1 as per the definition of the closed unit sphere in norm linear space. Then norm tx, here x is the element of S, then norm tx, we have norm tx less or equal to k norm x, and here norm x less or equal to 1, it means norm tx less or equal to k for all x belonging to S. This implies that the image Ts is bounded set in N dash. Conversely, let Ts is bounded, then we have to prove that T is bounded linear transformation. Okay, let Ts is bounded so that there exists a real number k greater or equal to 0 such that norm Tx less or equal to k, okay, for all x belonging to S. If x is equal to 0, then Tx is equal to 0, okay, because here x is equal to 0, taking the transformation of both sides, then Tx is equal to T0, and T is linear, so T0 is 0, that is Tx is equal to 0, okay, and so clearly norm Tx less or equal to k norm x, that is equality case, here for x is equal to 0. If x not equal to 0, then x upon norm x belonging to S. Okay, here x is the element of S. Then also we know that alpha x also belonging to S. Alpha is scalar. So here norm x as scalar. So we can write x upon norm x is the element of S also. And therefore by equation 5, okay, so we can put x upon norm x at the place of x. So norm t of x upon norm x less or equal to k. So t is linear and norm x as scalar. So we can write norm x out of tx because we know that t alpha x equal to alpha tx for scalar alpha. Okay, so here norm x as scalar. So we can write 1 upon norm x tx. Okay, again we know that norm alpha x equal to mod alpha norm x. Okay, so norm x always positive. So we can write outside this norm. Okay, that is this can be written as 1 upon norm x and norm tx less or equal to k. Okay, this one. This implies that norm tx less or equal to k norm x, that is cross multiplication. Thus, it is shown that norm tx less or equal to k norm x for all x belonging to n. Hence, T is bounded and the proof is complete. In this lecture, we have discussed the Banach algebra and further theorems of bounded linear transformations. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narisi. Second, introductory function analysis with applications, John Valley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.